Yeah, in fact, the whole power of quantum computers is because it computes in the multiverse.
Google's new quantum chip, Willow, just did something that shouldn't be possible.
We exist in multiple states. So when I see myself in a mirror, I say to myself, I'm looking at an average. An average because the real me is hovering over all different possible states. Some of these states are on Mars, on Jupiter. Most of the states are right there in my living room, but this is how I think. And that's how quantum physicists think. We calculate the probabilities of living in a multiverse of universes. And I say to myself, this is reality because we exist in multiple universes. That is the power of quantum computers.
It didn't just solve a math problem. It shattered a timeline. In less than 5 minutes, this chip completed a calculation that would take the world's most powerful classical supercomputer frontier-class machines that burn megatees of power, roughly 10 septillion years to finish. Stop and think about that number. That isn't just a long time. That is trillions of times longer than the age of our entire universe. If you started that calculation at the Big Bang, you wouldn't even be a fraction of the way through it today. And yet, Willow did it while you were making coffee. This performance is so extreme, so statistically absurd, that some physicists are whispering that it only makes sense if our reality isn't alone. They argue that for a chip to do this much work in this little time, it can't just be computing here. It has to be computing everywhere, across parallel timelines, across the multiverse.
Spider-Man exists in the multiverse. All the Spider-Man movies are now in the multiverse, where Spider-Man exists in multiple states of reality. Look at the Oscars. The big winner last year was Everything, Everywhere, All at Once.
But there is a catch, a massive one. Because while everyone is looking at the multiverse headlines, they're missing the real discovery. Hidden in the data is a pattern that suggests something even stranger about our universe. Something involving time flowing backward, invisible mirror worlds, and a ghost particle that might finally explain dark matter. Today, we are going deep. We're going to tear apart the hype, look at the actual engineering inside Willow, and then ask the biggest question of all. Did Google just build a computer, or did they build a window into a parallel reality? Let's dive in.
Well, remember when your mother used to say to you, you cannot be two places at the same time?
That's not true.
She was wrong.
She was.
You can be many places at the same time.
I have been lots
That's
of places.
called quantum mechanics.
What is Willow? First, let's ground this. What exactly is Willow? If you look at the headlines, you'd think it's a magic box. It's not. It is a masterpiece of engineering. Willow is Google's latest superconducting quantum processor, packing 105 qubits. Now, if you're used to hearing about gigabytes and terabytes, 105 sounds pathetic. My toaster probably has more processing power, right? Wrong. In the quantum world, 105 qubits is enough to break the known laws of computing. Classic computers, like your phone or laptop, think in bits. A bit is a switch. It's either on 1 or off 0. It's heads or tails. Even the most powerful supercomputer is just billions of these switches flipping really, really fast. Quantum computers don't flip coins. They spin them. Thanks to a property called superposition, a qubit isn't just a 1 or a 0. It's a complex combination of both states at once. It holds the potential of being 0 and the potential of being 1 simultaneously. When you link 2 qubits together, you don't get 2 states. You get 4. Link 3, you get 8. This scales exponentially. By the time you get to 105 qubits, the number of simultaneous states that chip is exploring is larger than the number of atoms in the visible universe. That is where the power comes from. A classical computer walks through a maze one path at a time. It hits a wall, turns back, tries again. A quantum computer floods the maze like water, exploring every possible path simultaneously. But for decades, there has been a problem, a fatal flaw that made quantum computers useless for anything other than party tricks. The below-threshold breakthrough. The problem is that qubits are divas. They are incredibly fragile. A stray photon, a slight vibration, a tiny fluctuation in temperature, literally anything touches them, and poof. The superposition collapses. The calculation fails. This is called decoherence. For 40 years, skeptics have said, "You will never build a useful quantum computer because you can't fix the errors faster than they happen." It's like trying to build a house of cards in a wind tunnel. The bigger you build it, the faster it falls down. This is where Willow changes the game. And honestly, this is the part that should be getting the headlines, not the multiverse stuff. Google's team didn't just add more qubits. They achieved something called operating below the surface code threshold. Here is what that means in plain English. Usually, in any complex system, adding more parts adds more problems. If you have a noisy radio signal, adding more noisy amplifiers just makes it louder noise. But Willow demonstrated the opposite. When Google grouped their physical qubits together to form a logical qubit, a virtual, error-protected unit, they found that as they made the group larger, the error rate went down. They moved from a 3x3 grid to a 5x5 to a 7x7, and every time they scaled up, the errors dropped exponentially. This is the Wright brothers moment for quantum computing. It proved that if we just keep building bigger chips, we can eventually make the errors vanish for all practical purposes. They have turned the wind tunnel off. The house of cards is standing. And because the house is standing, Willow could run that random circuit sampling task for long enough to leave classical supercomputers in the dust. But how did it actually find the answer? The metaverse argument. This brings us back to the 5 minutes versus 10 septillion years. When Willow runs this algorithm, it isn't just calculating fast. It is manipulating a probability landscape so vast that writing it down would require more memory than exists in all the hard drives on Earth combined. So, where is that information stored? If the chip only has 105 qubits, where are the trillion variables describing that complex state? Enter the many worlds interpretation of quantum mechanics. Proponents of this theory, like the legendary physicist David Deutsch, argue that quantum mechanics is telling us something literal about reality. They say there is no collapse of the wave function. Instead, every time a quantum event has multiple possible outcomes, all of them happen. The universe branches. In this view, our reality is constantly splitting into an infinite number of parallel timelines. In one timeline, the electron spins up. In another, it spins down. In one, you clicked this video. In another, you scrolled past. Now, apply this to Willow. If the many worlds interpretation is true, Willow isn't a single computer sitting in a lab in Santa Barbara. It is a multidimensional machine. When it enters superposition, it differentiates into countless versions of itself across those parallel branches. Each version of Willow in each universe does a tiny piece of the work. And then, through a process called interference, they combine those results back into a single answer that we can read in our timeline. Think about that. It implies that the only reason quantum computers work is that they are outsourcing the heavy lifting to their clones in parallel universes. We are essentially harnessing the computational power of the multiverse to solve our math homework. It's a seductive idea. It explains the magic. It explains how a tiny chip can outperform a planet-sized supercomputer. But here is the skepticism. Not everyone buys this. In fact, many physicists hate it. Critics, like Sabine Hossenfelder, point out that you don't need parallel universes to explain the math. The equations of quantum mechanics work just fine, without assuming those other worlds literally exist. They argue that superposition is just a mathematical description of our ignorance, or a property of a single, very weird universe, not a passport to Narnia. Just because the math looks like branching paths doesn't mean the branches are real places with real people on them. However, whether you believe in the multiverse or not, Willow has proven that reality at the quantum scale is fundamentally different from the reality we perceive. It is fluid, it is negotiable, and this fluidity isn't just happening inside a computer chip. It might be happening to the entire universe. And this is where we have to pivot. Because while the tech world is obsessed with Willow's qubits, a different group of physicists is looking at the cosmos and realizing that our timeline might be hiding a mirror image. If you thought parallel universes were weird, wait until you hear about the CPT symmetric universe. Because unlike the many worlds theory, which is almost impossible to prove, this one makes a prediction we can actually test. And Willow might be the first step in understanding the physics that makes it possible. The anti-universe. For decades, we have assumed the Big Bang was a starting gun, a moment where time began and everything rushed forward. But physicists like Neil Turok at the Perimeter Institute are asking a simple, dangerous question. Why would the universe be lopsided? In physics, nature is obsessed with symmetry. If you have a positive charge, there is a negative charge. If you have a north pole, you have a south pole. There is a fundamental rule called CPT symmetry. It states that the laws of physics should remain exactly the same if you do three things simultaneously. C, charge. Swap particles for antiparticles. P, parity. Invert space, like looking in a mirror. T, time. Reverse time. Our universe, on its own, breaks this symmetry. We have time moving forward, not back. We have matter, but almost no antimatter. It's messy. It's unbalanced. Turok's solution is radical in its simplicity. He suggests we stop looking at the Big Bang as a start. Look at it as a reflection point. Our universe extends forward in time. But on the other side of the Big Bang, extending backward in time, is our twin, a mirror universe. In this anti-universe, time flows in reverse relative to us. Left is right. Matter is antimatter. Crucially, this isn't a parallel dimension from sci-fi. It is a mathematical necessity to balance the equation of existence. Together, our universe and this mirror twin form a single, perfectly symmetric CPT system. And the scariest part? This model doesn't just look pretty. It fixes the biggest hole in modern physics without needing string theory or inflation. The ghost particles. If this mirror universe exists, it solves a mystery that has haunted astronomers for 80 years. Dark matter. We know something invisible and heavy is holding our galaxies together. Stars on the edge of galaxies orbit way too fast. They should be flying off into deep space. The only explanation is that there is 5 to 6 times more mass in the galaxy than what we can see. For 40 years, we've been hunting for exotic particles called WIMPs, weakly interacting massive particles. We've built multi-billion-dollar detectors deep underground in gold mines and inside mountains, waiting for a WIMP to hit an atom of xenon. And for 40 years, silence. Not a single detection. The CPT mirror theory offers a shocking answer. We've been looking for the wrong thing. We don't need to invent new particles. We just need to look at the ones we already have specifically. Neutrinos. These are ghost particles that pass through your body by the trillions every second. But here is the weird thing about neutrinos in our universe. They are all left-handed. Every single one we have ever detected spins to the left relative to its motion. This makes no sense. Electrons have right-handed versions. Quarks have right-handed versions. Why are neutrinos only lefties? In the mirror universe theory, the right-handed neutrinos do exist. But because of the symmetry, they live primarily in the mirror sector or were produced in the early universe in a state that makes them incredibly hard to see. These right-handed neutrinos would be fundamentally different. They wouldn't interact with the weak nuclear force like our normal neutrinos. They would be sterile. They would be heavy, stable, and invisible. But they would still have gravity. If the universe created huge amounts of these right-handed neutrinos at the Big Bang, they would still be here today, floating through space, clustering around galaxies, exerting a gravitational pull on stars, but remaining completely invisible to our telescopes. Invisible. Heavy. Everywhere. That is dark matter. We don't need magic. Dark matter might just be the ghosts of the right-handed neutrinos required to balance the CPT symmetry. It is the missing half of the particle family, finally showing up to balance the books. The smoking gun. Now, you should be skeptical. Mirror universes and time travel sound like hype. They sound like the kind of theories that are impossible to prove, relegated to the realm of philosophical debate rather than empirical science. Usually, theories like this, string theory, for example, are criticized because they are untestable. You can't build a particle accelerator the size of the galaxy to prove them, and their predictions are often beyond our current experimental capabilities. But the CPT mirror universe is different. It puts its neck on the line. It makes a concrete, brutal prediction that we can actually test right now, with existing or near-future technology. This is the hallmark of a truly scientific theory. Falsifiability. For the math of the CPT universe to work without breaking, one of the three known types of neutrinos must be massless. Here is the situation. We know neutrinos have mass because they oscillate. They change flavor as they travel through space, which is only possible if they have mass differences. This phenomenon, discovered in the late 20th century, was a huge breakthrough, proving that neutrinos are not massless as once thought. But we don't know the absolute mass of the lightest one. We only know the differences between their masses. Experiments like Katrin in Germany are currently trying to weigh neutrinos with unprecedented precision by measuring the energy spectrum of electrons emitted in tritium beta decay. Simultaneously, large-scale cosmological surveys are measuring the clumpiness of the universe, which puts an upper limit on the sum of neutrino masses. These two independent lines of inquiry are converging on the same fundamental question. This is the smoking gun. If these experiments find that the lightest neutrino has any mass at all, even a tiny fraction of an electron volt, the CPT theory is dead. Turok is wrong. The mirror shatters. The elegant symmetry collapses, and we're back to square one, searching for new physics to explain the universe's imbalances. But if they find a zero-mass neutrino, it would be the strongest evidence we have ever found that our reality is just one half of a whole. It would mean that the Big Bang wasn't a messy explosion, but a perfect crystalline reflection point. It would mean that time really does run backward somewhere else, and that our universe is part of a grander, symmetrical cosmic dance. This single experimental result would revolutionize cosmology, particle physics, and our understanding of existence itself. We are literally waiting for a number to drop that will decide the fate of this theory. And that number is coming in the next few years. the tension in the scientific community is palpable. So, why does this matter? Why connect a Google chip to the Big Bang? Because we are living through a unique moment in history, where our tools and our theories are converging on the same impossible idea. That reality is not local. It's not confined to the single, observable universe we inhabit. This convergence of cutting-edge technology and theoretical physics is pushing the boundaries of human knowledge. On one side, we have Google's Willow, a machine that proves our classical understanding of computing is incomplete. To explain its power, we either have to accept that it computes across a multiverse of parallel states, or we have to rewrite the rules of information itself, perhaps even challenging the very foundations of quantum mechanics. It's a technological marvel, forcing a philosophical reckoning. On the other side, we have the CPT mirror, a theory that suggests our entire 14 billion-year history is just a reflection in a cosmic glass. It suggests that the missing pieces of our universe, antimatter, dark matter, right-handed neutrinos, aren't missing at all. They are just on the other side of the mirror, completing a grand cosmic symmetry. This theoretical framework offers an elegant solution to some of the most persistent puzzles in cosmology. Whether we are hacking the multiverse with superconducting qubits or mapping it with symmetry equations, the message is the same. The universe is simpler, stranger, and far more vast than we dared to imagine. It's a universe where the impossible becomes plausible, and the boundaries of reality are constantly being redrawn. We used to think we were the main characters of the story. Now we are realizing we might just be half of the equation, part of a larger, interconnected cosmic tapestry. This shift in perspective is humbling, yet exhilarating, opening up new avenues for scientific exploration and philosophical contemplation. If you want to understand the other technology that's breaking physics, then hit that bell icon to get notified when we post a new video.